There are places in the universe where the laws of material science, as we probably are aware them, are nearly obscured. Time twists and space contains hundreds of years before an apple fell, and with it, the seeds of Sir Isaac Newton's gravitational hypothesis were sown. It was a basic truth, an apple drawn to the earth. Yet, it uncovered an infinite significance that ties the universe together. Inside that significance, however, sneaks a huge hole, areas of strength for so no known molecule can leave it. This is the domain of dark openings, enormous secrets that have baffled stargazers, physicists, and logicians for many years. Suppose you will, a frenzy in the texture of space-time so strong that even light can't avoid its draw. This is the occasion horizon, the point of no return. It is here, at the very heart of this enormous anomaly, that the idea of singularity is seen as the point where mass is accepted to shrivel to limitless thickness, and the laws of physics break down under the heaviness of its difficulty. Yet, consider the possibility that all that we use to ponder these dark monsters is possibly part of reality. Imagine a scenario where the solitary clarity, that place of boundless thickness and zero volume, isn't the unavoidable finish of a dark opening center. Late exploration has started to lift the shroud on this strange peculiarity, scrutinizing the actual thought of a singularity and proposing a reality far more complicated and, surprisingly, more puzzling. Join us to attempt to make sense of this issue together. At the actual heart of the 20th century, as physicists dug ever deeper into the texture of the universe, a momentous hypothesis arose that established its spot in the annals of material science. Sir Roger Penrose, a visionary English physicist, presented the world to Penrose's singularity hypothesis, which tested how we might interpret the universe and its generally strange elements, dark openings. This hypothesis, introduced in 1965, uses the numerical foundations of the general theory of relativity to offer a significant expression about the nature of dark openings and the certainty of singularities in them. Penrose's hypothesis depends on an underhidden standard of Einstein's general theory of relativity, which portrays gravity not as a force in the conventional sense but as a bend of space-time caused by mass and energy. According to the general theory of relativity, huge objects like stars and planets twist the texture of space-time around them, influencing the movement of objects and, surprisingly, the way of light. Penrose's singularity hypothesis states that under certain logical circumstances, specifically the presence of what he called a trapped surface, where light beams unite instead of separate, a singularity, a district of the endless shape of spacetime, should form inside a dark opening. This locked surface marks the final turning point beyond which all ways unavoidably lead to the singularity, the spot where the known laws of physics stop working. One of the most striking outcomes of Penrose's hypothesis is the idea of geodesic incompleteness with regards to spacetime. A geodesic is the shortest way between 2 points, like a straight line in curved space. Penrose's hypothesis proposes that inside a dark opening, some of these geodesics cannot be infinitely extended into the past or future, demonstrating the limit of spacetime itself. The singularity. Imagine you're floating in a kayak on a quiet, wide stream, and it represents the universe. The stream's current, its consistent flow and direction, mirrors the ways in spacetime known as geodesics, along which planets, stars, and light move due to gravity. As you swim further, you approach a region where the stream current becomes increasingly violent. Ahead is a tremendous secret cascade, hidden in fog. Cascade seems to be a dark opening where the water starts to fall. Descending looks like an occasion skyline, a limit past which there is no return. As the water moves toward the falls, the flows that used to stream equally start to join and advance quickly toward the edge of the falls. Notwithstanding the speed of the water and the strength of the waterway, neither can get away from the draw of the cascade when it arrives at the bluff. This union of the streams ebbs and flows at one point, yet never arriving at a stable end, outlines the idea of geodesic deficiency close to a peculiarity inside a dark opening near the skyline. A photon kayak, attempting to swim straightforwardly against the ongoing, just waits, regardless of how much you try, but you'll never swim anywhere. The flows of space, coordinated inward, totally kill your movement. Inside the skyline, the vast cascade falls faster than the speed of light, taking everything with it. The water, addressing the ways of particles in light, doesn't just stop or psychologize. Maybe the idea of the waterway space, the actual scene, changes significantly at the cascade. The ways of water are constrained to unite and lower, in light of the construction of the cascade, analogous to how space-time around a dark opening is distorted so strongly that all ways are unyieldingly pulled toward a peculiarity. The implications of Penrose's work were significant. If singularities truly do exist inside dark openings, then broad relativity, our best hypothesis of gravity, and the huge-scale design of the universe are in fundamental conflict with quantum mechanics, the theory governing the subatomic world. This contention, known as the quantum gravity issue, remains one of the main challenges in modern physics. In 2020, the Nobel Prize in Physics was awarded to Roger Penrose for his discovery that the formation of dark openings is a strong prediction of the general theory of relativity. The honor not only recognized Penrose's pioneering work but also highlighted the critical role of singularities and the profound, unsettled tensions between the pillars of modern physics, specifically accommodating the vast size of the universe with the infinite quantum domain. In the chronicles of dark opening theory, one name stands out for extending our understanding of these vast secrets: Roy Kerr. This New Zealand mathematician offered a revolutionary perspective that forever changed the scene of astronomy. Kerr's pioneering contribution was the Kerr metric, a solution to the equations of Einstein's general theory of relativity that describes the space-time surrounding a rotating dark opening. Unlike the static, non-rotating black holes imagined by Schwarzschild, Kerr's black holes were bursting at the seams with spin, reflecting the dynamic, rotating universe we observe. One of the most intriguing results of Kerr's work on rotating black holes is the presence of the ergosphere. This is a region just past the event horizon, where the rotation of the dark opening twists space-time itself, pulling everything alongside it. Here, the very fabric of the universe moves to the beat of the black hole's spin, testing our conventional ideas of space and movement. In the ergosphere, the laws of physics work in a strange and captivating way. Particles in light can advance to colossal speeds, gaining energy from the spin of the black hole. This phenomenon fires the imagination, suggesting the possibility, albeit theoretical, of harnessing the energy of dark openings, a concept that was once consigned to the domain of science fiction. Perhaps the most revolutionary aspect was Kerr's reimagining of the singularity at the center of the black hole. Gone was the idea of infinite density at the core of the black hole. In its place, Kerr proposed a ring. Peculiarity, a circle of limitless thickness and gravity, an idea that expands the limits of math. Such a view was not only a numerical victory, it was a paradigm change in a universe moving through dark openings, turned enlivened by something very similar: powers that pivot planets, stars, and galaxies. So, at the core of our concern is a subtle understanding of the ways that particles and light take geodesics through curved spacetime around black holes. The traditional thought expressed that these ways, the geodesics along which light ventures and the directions of matter, definitely lead to a peculiarity, a point of endless thickness where the laws of physics as we presently know them break down. Anyway, a progressive point of view has arisen in a new study on Kerr. It contended that the idea of geodesic deficiency that passes in a spacetime should end in a peculiarity inside a black hole is based on confusion. He argued that, while the numerical boundaries describing these ways might be limited, this doesn't necessarily imply that spacetime itself is unraveled into a peculiarity. According to Kerr, the ways of light inside a black hole, represented by zero-point geodesics, could, for sure, be limited by the event horizon of the black hole. However, this limit didn't connote the finish of spacetime or the inevitable presence of a peculiarity. Rather, Kerr proposed that these limited directions could exist in the complex structure of a black hole without requiring the presence of a singular point with infinite thickness. In addition, the dog metric presented the idea of an event shell, distinguishing it from the event horizon, and proposed that directions inside this shell are impacted by the precise energy and mass of the black hole, allowing for a range of behaviors not previously considered. At the core of this study is the striking difference between the Schwarzschild black hole, described by a point peculiarity, and the Kerr black hole, with its mysterious ring peculiarity. This ring, born of the black hole's spin, extends the peculiarity along its axis, making a design considerably more complex than the solitary point imagined by Schwarzschild. The ring peculiarity of the rotating black hole opens up a range of possibilities where the paths of light and matter are not destined to a singular end but can circle and twist around this gravitational vortex. This remarkable design allows for the hypothetical possibility of pathways through the ring, potentially leading to gateways to different regions of spacetime or even unexpected infinite peculiarities. When a rotating black hole turns, it traps spacetime, even distorting the very fabric of the universe. This edge-hauling effect distorts the directions of light and matter, making them spiral around the black hole and deviate from the straight-line plunge into the peculiarity imagined in a non-rotating model. In this maelstrom of twisted spacetime, theoretical models suggest such extraordinary peculiarities as closed time-like curves, paths that can hypothetically return to their past, invoking our concept of time. Additionally, Las K's observations present a serious challenge to Penrose's hypothesis. If rotating black holes, with their peculiarity-evading geodesics, are more than just a numerical curiosity, if they are a real feature of our universe, then the universality of Penrose's hypothesis is under question. The presence of paths inside the peculiarity-evading black holes points to a reality far more perplexing than a simple point of no return and demands re-examining current hypotheses. Against this reassessment, the search for a unified theory of quantum gravity continues as the theory that will ultimately connect quantum and astronomical scales. It's minute and incredibly vast. Hopefully, this will bring about a new understanding, and perhaps theoretical physicists can relax with a small sigh of relief, no longer being so restricted by the confines of space-time singularities.